Welcome back, ladies and gentlemen. This is the second day of 10.7, graphing circles on a coordinate plane. Up on the screen, as usual, you'll see your exit question for the day. I want to start off by actually graphing a circle. That's something we didn't do last time. Last time we figured out where the equation for a circle came from, how it was derived, and how to get the basic information out of an equation. And that's what I'd like you to do with this equation up on the screen right now so we can start graphing it. If you can get where the center is and where the radius is out of that equation, that'll help you a lot in drawing it. So see if you can do that right now. If you do that correctly, given its h, its k value, and by taking the square root of the right-hand side of the equation, you get the center is at 3, 4, and it has a radius of 5. And in order to graph this circle, that's exactly the information we need. So we go ahead and we plot the center, and then we try to plot all the points that are exactly 5 units away from that center. Now that's very difficult to do in many places, but there are 4 places in which it's very easy to do, and that would be just directly above, below, to the left, and to the right of it. So you can see those 4 points plotted there. Now when you go to graph a circle on your homework or on a test or whatever, those 4 points are all that I am going to require. You can just do your best to help sketch the circle in its entirety around those 4 points, or even better yet, use a compass to connect them all. But in this particular case, there's a way to cheat and get a few more points. You'll notice that the radius is 5 in this case, which is the hypotenuse of our very favorite 3, 4, 5 Pythagorean triple, which means that just by drawing a few right triangles, 3, 4, 5 right triangles, you can get an additional 8 points along this circle. So you can see how I've sketched those out, and that just helps you give a little bit better guidance. Connect the points, and you've got yourself a circle graphed properly. The next type of problem that the book might ask you is to write equations for lines, linear lines, that have certain properties. In this case, a secant going through the diameter or containing the diameter, a tangent line to the circle, and just any old secant line. Now technically there are an infinite number of ways to do each one of those items, but there are a limited number of ways to do each one of those items easily. So I want you to pause the video and see if you can come up with some equations for lines that fit the bill per those specs right there. And if you've done that, well, let's start off with the secant contained in the diameter. There's 2 easy ways to do that, and that would be with a pure horizontal line and a pure vertical line. And if you've forgotten how to write an equation for those, think of this line. This is y equals 4. That is the line that contains all the coordinates where they have a y coordinate of 4. And this is the line x equals 3. It's the collection of all points where it has an x coordinate of 3. Next one up is a tangent line, and there's a lot of places you can draw a tangent line on a circle, but there are 4 places in particular that are more easily done, at least if you avoid using complicated mathematics. So on the far right, far left, far top, and far bottom of the circle, you can draw a tangent line that just touches the circle in one place, so long as you know what the x coordinate is going to be right here, and we do, because it's going to be 5 units away from here. So that line right here has a equation of x equals -2, and by the same reasoning you can go y equals -1, and so on and so forth. The secant line is the most open-ended one because it didn't really give you any other information. It just has to intersect the circle in 2 different places. So that's pretty easy. It's open-ended. Here's just one example: slope of 2 and intercept of 3, and that's all it takes. Now, as a test to see how good you are with these equations for a circle, the book's going to ask you a couple questions like this, where they give you a basically big jumbled up mess of variables and constants, and see if you can determine whether that's a circle or not. And you can see by looking at this one, it has some of the key features of an equation of a circle. It has an x squared term, it has a y squared term, and there is a constant off to the right. Now, the only other issue here is that you don't see in the basic formula for a circle is this term right here. There's nothing here that has an x times a constant, but since you've all been foiling and factoring forever, you'll probably recognize that it would be pretty easy to get a 10x out of this if it were the result of FOIL, which in this case we can try to do. Now, if this 10 came from the result of being FOILed, that would mean that it would really be, and remember we're squaring the same thing over, So whatever that number is right there, it would be repeated twice. So it would be half of this number, which would be a -5. And if you took a -5 times -5, you would get a +25. And you'll notice we don't have a +25 here, we have a +30. Well, that's not such a big problem because we can split that 30 into a 25 and a 5. And then this 5 ends up collecting out here basically on the garbage side of the equation, just so that we can factor this trinomial right here with all of our x's. And if you do that, you get x minus 5 squared plus 5 plus y squared equals 64. Then you just move the 5 over there, and then it looks a little bit more like the equation for a circle. You can see that this has a center at 5, 0, because it's like a y minus 0 right there. And even though we've gone from a perfect square to something that's not a perfect square, the square root of 59 is still a number, and it is still a distance, and so it still can be a radius. So this particular circle has a center at 5, 0, and a radius of the square root of 59, just like that. Our next problem looks a good deal messier. You'll notice that it has more terms to it, and frankly, they could have made it a lot more difficult. They could have taken that 4 and combined it with this 12, and they could have taken both those numbers and brought them over here. But it's the same basic technique. We know that if it is a circle, then we took the same thing and we squared it. So our h term, for instance, would be half of whatever's with the x, and our y term, or our k term, would be half of the term that is with our y. And you notice over here that works out nicely because half of -4 is -2, and -2 times -2 is +4. So look at that, that's all ready to go for us. However, when we get over here, half of 6 is 3, and 3 times 3 would be 9, so we really want this to be a 9. Not such a big deal, we can group those together. We know that that x trinomial is going to factor just nicely. But we'll take the y one and we'll split that 12 into a 9 and a 3 and kind of think of it in that term in our head. And then we can factor that, of course, which looks something like that. And once you have that y trinomial factored, then we have this leftover 3 that we can just tack on to the other side. And then we do get a perfect square, so we have a radius of 7 and a center at 2, -3. Here's your assignment the next time I see you, and I'll see you next time.